Alright, so thanks for the introduction, Frank, and hello everyone. In my talk today I would like to give you an introduction to quantum software engineering, a topic that gains a lot of attention from research and industry at the moment, and thereby I will also show you some concepts and tools that we developed at the Institute in this research area. But first I would like to start with a short motivation why we need software engineering for quantum applications. And recently there were various breakthroughs in quantum computing, such as reducing the error rates of the operations that are executed in quantum computers, for example. And furthermore, different providers, such as IBM or Google, released ambitious roadmaps containing goals in the scaling and improvement of their hardware over the next decade, and Frank already showed you briefly the roadmap from IBM, for example. So there's an increasing need to develop new quantum applications, and these quantum applications should be developed following a clear process to increase their quality, which is the goal of quantum software engineering. And on the other hand, various experts are required to applications. So for example, we need computer scientists to develop the software, physicists and mathematicians to develop new quantum algorithms and circuits and so on. And all these experts need a common understanding of how to develop and operate such quantum applications. And exactly this is the goal of quantum software engineering. And in classical software engineering, we usually use life cycles to develop or to document these different phases, tools and concepts, which should also be applied to quantum computing. And therefore we need a life cycle for hybrid quantum applications, to which we refer to as the quantum software life cycle. And in this talk, I would like to show you our proposal for such a quantum software life cycle. So as quantum applications are always hybrid, first we need a life cycle for the classical software artifacts of the application. Thereby, a plethora of the life cycles were proposed in the literature, such as the V model, the spiral model, the prototype model, and so on. And in addition, we also need a life cycle for the quantum programs, and we restrict ourselves at the moment to the quantum circuit model, and therefore we need a life cycle for quantum circuits. But also in the future it could be integrated life cycles regarding other programs following another quantum computing model, such as the adiabatic, for example. Then all these classical and quantum programs must be orchestrated, and this orchestration is done using workflows. And for this we extend the existing life cycles for workflows existing in the literature for the quantum computing domain, leading to this quantum workflow life cycle here. Following the DevOps paradigm, we have to tightly integrate the development and operation of the different software artifacts to enable fast releases, which is especially important in the quantum computing domain, as it is a rapidly evolving field which recently releases new hardware, new software, and so on. So finally, all these sub-life cycles must be played together, and how this is achieved is defined through this outer life cycle here, consisting of 8 phases. And on the following slides of my presentation, I would like to zoom into multiple of these phases, as well as sub-life cycles, and discuss corresponding problems, tools that are available to solve them, and also conceptual methods that could be used to solve these problems. But as you can see here, already the outer life cycle has 8 phases, and also the sub-life cycles have multiple phases, thus I can only cover a small subset of them in my presentation now. But I'm happy to also answer questions regarding other phases if you're interested, either in the Q&A or also offline afterwards. And additionally, if you have questions in between, just interrupt me, and then I will try to answer them, as we cover quite heterogeneous topics, and therefore it could be good to discuss that directly. So this life cycle starts with the requirement analysis phase, and similar to classical software engineering, it's intended to identify and document all the functional and non-functional requirements for the hybrid quantum application. Then we come to the quantum classical splitting phase, and this is the first phase in which I would like to zoom in now. So it gets the requirements from the previous phase as input, and is intended to decide which parts of the problem to solve on a quantum computer and which on a classical computer. This involves, for example, determining algorithms that can be used to solve a problem or problem part, and evaluating their suitability. And when determining this, there are different dimensions that should be taken into account, such as the speed up that can be achieved, accuracy, or also the energy efficiency, for example. Furthermore, it must be evaluated if today's quantum computer is already powerful enough to solve the problem with the intended input size. Today, this is usually done manually by experts based on their experience and knowledge, but a first step into automating this, or also helping the user in this decision, is a tool to compare and evaluate different quantum and classical algorithms called Johanna, and that will be presented by Johanna in the next talk today. Finally, this can lead to an automated recommender, which can, for example, be based on provenance data, as we will see at the end of my presentation, or also be based on patterns, and which pattern exists in quantum computing domain will also be part of the next talk by Johanna. So after we perform the quantum classical splitting, we can define the architecture of the hybrid quantum application, which is based on the components and the interplay that are in this architecture are based on this quantum classical split. Then this architecture is iteratively refined until we get to a design that contains all the required details to implement the different software artifacts of the quantum application. So this means in the implementation phase, we now enter these sub-life cycles here in the middle to develop the different software artifacts that we need for our application. And as the first sub-life cycle that I would like to discuss today is the quantum workflow life cycle. These quantum workflows are intended to orchestrate the data and control flow between the different other software artifacts. And the life cycle of this quantum workflow life cycle consists of 8 phases. And next I would like to discuss the modeling as well as the quantum classical splitting in more detail. In the modeling phase, we define or model the abstract workflow model containing different activities, the partial order and the data flow between them. But it's not yet defined how these activities are implemented. The first step in this direction is the quantum classical splitting, where we now decide on that activity level which activities involve the processing on a quantum computer and which require only classical processing. So, exactly, to explicitly define these activities that require quantum actions or quantum-related activities, we introduced the quantum modeling extension, or QuantMe for short. QuantMe is a modeling extension for imperative workflow language, and in the following we use the DPMN concepts and that graphical notation to define this. Thereby, QuantMe has the objective to ease the modeling of workflows, orchestrating quantum circuits, and also to increase the reusability of software artifacts implementing different frequently occurring steps by introducing explicitly modeling constructs for them. So, for example, if we have a look here, you can see that QuantMe introduces a data preparation task for this data preparation step Frank already mentioned. We have a task to execute quantum circuits on a quantum computer, or also a mitigation task to perform the mitigation after the execution of the quantum circuit. In addition, each of these tasks provides a set of configuration properties which can be used to customize the task depending on the need in the workflow. So, for example, for data preparation task, we can define the encoding that's used to map the classical data into this preparing quantum circuit. Similarly, for the real-error mitigation, we could define the unfolding technique that should be used as there are multiple available with different benefits and drawbacks. So these tasks here on the higher level guide quantum experts in modeling workflows executing quantum circuits, but they are still complex for people that that are not really into quantum computing, and therefore we have another abstraction level on top here, which is intended to integrate complete predefined quantum algorithms which should with a single task into a workflow model. And the idea is that in the later life cycle phase, when we just specify the algorithm and the provider, and in the later life cycle phase, this task here is then replaced by a subprocess or a workflow fragment or reusable, which implements this required logic. So after this, after the modeling and quantum classical splitting, we are at the IT refinement, where we now select the complete implementations, the responsible persons for human tasks, also the services for the different activities to get from an abstract workflow model to an executable one. And this executable workflow model can now be further improved, which is the goal of this analysis and rewrite phase. So although workflows have multiple benefits if we orchestrate high quantum applications, we also have some drawbacks regarding the efficiency in some use cases. And we will discuss this using this example here, this example workflow, implementing a so-called variational quantum algorithm. So the workflow starts with initializing the quantum algorithm by loading or generating the ansatz, which is a parameterized quantum circuit, which the parameters are optimized in multiple iterations. Next, we execute this ansatz using the corresponding quantum task. Based on the results, a cost function is evaluated, and depending on the result, if the costs converge, the workflow terminates, or otherwise we will enter the next iteration. So if we enter the next iteration, we would optimize the parameters based on the previous results, and then start again with executing the quantum circuit. However, we can see two problems regarding the efficiency of the execution here. So first, today's quantum computer usually enable the access by using Q, That means in each iteration we have to put a job into this queue, then it waits for the execution, and finally the classical how to execute, for example, in the cloud, which was also the context of the question before. So exactly, so one possibility here would be to reserve a time slice for the exclusive execution on the quantum computer, because then we wouldn't have to wait in each iteration. However, this has the drawback that it's very hard to estimate the required execution time, and therefore this can lead to unused reservations with corresponding costs. And the second problem still remains, which is the communication between the quantum and classical parts. So this means in each iteration we have to transfer the data between the QPU and the cloud, which could be, which could take some time, and with a high set of iterations, the transmission times get very long then. So these parts have to be deployed closely together, and this is exactly the concept of hybrid programs, of hybrid runtimes, such as discrete runtime or Amazon rapid hybrid jobs, for example. So they enable to upload the quantum parts and the classical parts together, then deploy the classical parts close to the quantum computer, and optimize the communication between the quantum and the classical hardware. Furthermore, we only have to we only have one queue access then, and afterwards we can execute all the iterations of the variation and quantum algorithm. So we have here, we have a gap here between the benefits of modeling workflows and efficiency improvements if we use hybrid runtimes. And the goal of this lifecycle phase is to overcome this gap by analyzing the workflow and rewriting it to use these hybrid runtimes where appropriate. So for this, we developed the analysis and rewrite method consisting of 6 steps. It gets the workflow model that was modeled by the user in the previous phases as input, which could contain quantity tasks as well as modeling constructs of the used workflow language. Then we automatically analyze this workflow model and try to detect candidates that could benefit from a hybrid runtime, which is the case for 2 workflow fragments in this example here. Next, they are filtered based on the characteristics of the candidates, which could, for example, be the used modeling constructs, the corresponding implementations with the used languages, and so on, and also the capabilities of the different hybrid runtimes that are available. Afterwards, we generate then a hybrid program. So a hybrid program is the kind of software artifact that can be executed in these hybrid runtimes out of the candidates. And for this, we expect the implementations for the different tasks that are within these candidates and combine them into this hybrid program. So this is also one drawback, as we need the code, the source code of these programs, which can, for example, be achieved for script tasks, or can also be achieved by packaging everything in the quantum application archive as Rank proposed. But it could be difficult if you use service available over service registry, for example, if you cannot get the source code to it. So in the 5th step, then we rewrite the workflow to use these generated hybrid programs. This means all the activities within these candidates are replaced by a single service task, performing the call to this hybrid runtime. And in the last phase, the workflow, as well as all the required services and the hybrid programs are deployed, and finally the workflow can be executed. Alright, so the second software artifact for which I would like to show you the detailed view now are quantum circuits. These quantum circuits should be implemented in a hardware-independent manner to enable later hardware selection based on the properties of the circuit, such as the circuit size, for example. Then they can be tested or verified. Approaches exist. For example, if we only have small circuits, we can simulate them and verify the results classically. Or there are also approaches, for example, adding runtime assertions based on Agila qubits, but that's still very active research direction which needs some further concepts. And then until this phase, so during these phases, the quantum circuits are independent of certain input data or a problem instance to solve. And this is changed in the quantum circuit enrichment phase. So the quantum circuit enrichment phase has the goal to configure the quantum circuit to solve a specific instance of the target problem. And thereby we can divide it into 2 steps. First, the Oracle expansion, and second, the data preparation. An Oracle is a black box that is used by different quantum algorithms, such as Simon's or Grover's algorithm, for example. So for Grover's algorithm, the Oracle decides whether an element in a collection is the searched one or not. But if we want to execute this quantum circuit here, and then we see we have a placeholder for Oracle here, we have to replace it first by a corresponding subcircuit implementing its functionality, which is achieved by inserting this subcircuit here, for example. Another problem that Rank already mentioned is that we cannot load arbitrary data in the quantum computer, but we have to execute or we have to prepare the required state by the quantum circuit before the actual calculation starts. And this problem can be solved by implementing or generating an initializing circuit that is then prepended to the original circuit to prepare the state before the calculation starts. And for this, different encodings exist, which provide different benefits, such as a shallow initializing circuit, for example, or the possibility to encode more data into the register. And therefore, this decision which encoding to use is a very important choice. After the enrichment, we could now select a quantum computer for the execution of the enriched quantum circuit. And this will be discussed by Marie in another talk this afternoon, so I won't go into more detail here. But I would like to zoom into the next phase again, which is the optimization and compilation. One problem that we often have today is that we cannot execute the required quantum circuits because their size is too high, which means they require too many qubits, or the depth is too high, leading to high error rates and faulty results. One possibility to solve this is circuit cutting, where the main idea is to execute multiple smaller circuits instead of one large one, which could lead to better results in the end. So if we have a look at this example here, this large quantum circuit here cannot be executed. Therefore, we decide to split it into these two parts here, on the top the red one and the blue one on the bottom. Then we have to generate multiple variants of these parts and can execute them. This execution can be done in parallel if we have multiple quantum computers available. Finally, these results are then combined into the overall result from the large circuit based on classical post-processing. So, additionally, after the hardware selection, we have to compile the quantum circuits into the machine instructions that can be understood by the target quantum computer. And thereby, this includes the replacement of gates that are not natively supported by the quantum computer by a subset or by a subroutine of other gates that are implemented and that implement the same functionality. So these gates are then replaced during compilation. Another point is the allocation of the qubits, which means to map the qubits from the quantum circuits to the quantum computer. And as these qubits have very different characteristics, for example, the coherence times, the connectivities, this can largely impact the execution of the quantum circuit and the results that we get out there. So, for example, if we want to allocate the qubits from this quantum circuit here on the quantum computer with this topology, and we have some qubits on which multiple 2-qubit gates are executed, we should, for example, allocate them on Q0 and Q1 as they are directly connected, because this means we can directly execute 2-qubit gates, and otherwise we would have to insert additional swap gates, which would increase the overall circuit size, which could then result in higher error rates, for example. During this compilation, there's also some optimization done, and this optimization is quite complex and should take into account multiple properties of the quantum computer, such as the coherence times of the different qubits, the connectivities, or the gate fidelities or gate errors. Afterwards, then the quantum circuit can be executed, and finally error mitigation should be performed. The main idea, I think I can do it quite fast, as Frank already introduced the unfolding. The main idea is to reduce the impact of errors until error correction is available. And one simple example technique to apply is the calibration matrix, which consists of 2 steps. First, we have to generate some data by initializing all the 2 to the power of n basis states. Then we measure them. Based on the measurements, we get this approximated error model, and this can be used in the second step to move the probability distribution from a circuit execution to another probability distribution that should then be closer to the result without errors. So the last sub-life cycle is the operations life cycle intended to manage and operate all the others of the artifacts. And this life cycle starts with the topology modeling, which is intended to specify all the required details that are needed for later automated deployment of the hybrid quantum application. However, this comes with additional challenges compared to the deployment of classical software. The reason for this is that modeling principles that are common for the deployment of classical applications do not directly apply to some of the quantum cloud offerings. So, for example, if we would like to model a topology deploying a quantum program using the Tosca standard, we would model a quantum program here as a node and add another node for the quantum cloud offering to use, in this case IBM Q, and then that should be automatically deployed. However, one problem today is that we usually deploy the quantum circuits when we are to execute them. So instead, we would have to model a quantum program, which depends on KISS that itself requires a Python runtime, and finally would host everything on a virtual machine, providing an API to call these circuit invocations. And to ease the modeling of these topologies, TOSTA4QC was developed, which analyzes these two modeling styles on the left and on the right, and provides an automatic transformation between them. So the user only has to specify a simple model on the left, and then it can be automatically transformed into this model on the right, containing all the required details for the deployment. Afterwards, the quantum application can be packaged as quantum application archives to offer them, for example, over a platform such as Blank, which will be presented by Michael later on. Then we can deploy the application, and finally, in the final phase that I would like to discuss, we can observe or monitor them. So, to properly observe a hyperquantum application, we must collect very detailed data about the quantum application as well as the execution environment. And collecting such data about the process is referred to as provenance, and it has the goal to increase the reproducibility, understandability, and quality of the process. In the quantum computing domain, this is especially important as we still have noisy devices and very different technologies, and therefore we need detailed information, for example, to analyze occurring errors. And there are different example application areas exist. For example, we can use that for the quantum hardware selection that we will hear later today, or we could also periodically generate this calibration matrix for read order mitigation, or another example would also be the qubit allocation during the compilation, which can be optimized based on current data about the qubits of the quantum computer. So we have to analyze which attributes we should collect about the quantum applications and the execution environment, and for this we identified 4 different theories, and the first one comprises the quantum circuit, for example, documenting its size and depth for all width. Second, we have to collect data about a quantum computer, for example, the coherence times, their gate fidelities, their connectivities, and so on. Parts of this data have additionally be collected periodically as they change over time. So, for example, recalibrating the quantum computer, and therefore we have to collect them regularly. The third theory comprises data about the compilation, such as the qubit allocations that were performed or the gate methods. And finally, we also have to collect or gather data about execution, which, for example, comprises input data, output data, intermediate results, or also the number of iterations that were performed for a variation in quantum algorithm, as we have seen in the example before. All these data must be collected systematically, and for this we introduced a quantum provenance system called QProv, which periodically accesses the APIs from the providers to retrieve the data that's available there. And furthermore, it also executes calibration circuits to get data that's not available via the APIs, which is, for example, the case for this calibration matrix. Additionally, also other tools are used, such as the NIST analyzer or TOSTA, to retrieve data about the running quantum application, for example. And all this data is stored in a database, which can be queried, for example, to analyze the decoherence times, the evolvement, timely development of the decoherence times for a certain quantum computer. So this already leads me to my conclusion and the short outlook. So we have seen that for the development of hybrid quantum applications, we need experts from different fields, and all these experts need a common understanding of how to develop and operate such applications. So for this, a lifecycle can be used to document all the possible problems, concepts to solve them, and also for the tooling support. This lifecycle is multiple interwoven lifecycles, and on the one side for different software artifacts, such as the classical programs, quantum programs, and workflows, and also an operations lifecycle to operate all these artifacts. And for future work, there are many open problems for the different phases. So, for example, what I documented here, just quantum classical splitting needs further research, for example. And also we need tooling support for multiple of the phases. As quantum software engineering is still a relatively new field, there are really many open problems that need more research. And that could lead to new tools in the future. So that's it from my side. Thank you very much for your attention, and I'm looking forward to your questions.
Thank you very much, Benjamin. Questions?
Thanks. I find the part about the provenance really interesting, and I'm wondering where to draw the line between provenance and reproducibility, because most of this data you would also collect in order to make experiments reproducible. So where do you position yourself? Is it the same for you, or is it a different batch of data that you collect?
So it definitely includes the same sets, or at least the parts of the set. So reproducibility is definitely one of the major goals, which should be achieved by documenting all this data. But additionally, we can also, in addition to reproducibility, we can also document data that can lead to improvements in the application. So for example, we could see that a certain quantum computer was not suitable for executing a certain circuit, and therefore we can, based on this data, analyze the execution and then have some improvements in the quality. But definitely reproducibility is one of the major goals, yes.
Further questions? Yeah.
So in use cases, how big data are we talking about? Are they in gigabytes or small data?
So it's a bit hard to understand this.
How big data? How big is the data that we can process?
Okay, at the moment, not really big, but as Frank showed in this roadmap, so for example, IBM has the goal to achieve 1 billion qubits, I think, at the end of the decade, and then we can reprocess high data sets. And the other solution would be the variational algorithms I mentioned. So there we can solve some optimization problems, for example, and then we can also operate on data sets. But for example, for the HHL algorithm that was also mentioned by Frank, it is not really realistic at the moment to execute that for reasonable data sets.
Further questions? If not, then first, thanks again. Thank you very much. The first slide, what we typically do is those presenters that are willing need to share their slides. We will put them into the Dropbox, I think. And we always take videos of the talks and we'll share them links with you. So if you would like to see them. If you don't want to send your slides, it's absolutely fine. And if you don't want a video be taken, let us know, then we switch it off. Otherwise, by default, we